Explanation: a first-order linear ordinary differential equation, ODE, can always be written in the standard form. dy by x plus p of xy equals q of x. Where the unknown function is y of x, p of x and q of x are known functions of the independent variable x. The word linear means that y and its derivative appear only to the first power and are not multiplied together. How to recognize p of x and q of x: bring every term containing y or dy by x to the left-hand side. Make sure the coefficient of dy by x is 1. Divide the whole equation by that coefficient if needed. The remaining term that multiplies y is p of x. Anything that does not involve y or dy by x on the left becomes q of x after moving it to the right. Real-world analogy: think of a water tank where the rate of change of water level dy by x depends on two things: a leak proportional to the current level, that is p of xy, and an inflow that may change with time, that is q of x. The standard form separates the leak loss from the inflow gain. The integrating factor is a clever trick that turns the left-hand side of 1 into the derivative of a product, allowing us to integrate easily. Start from 1. dy by dx plus p of xy equals q of x. Multiply every term by an unknown function mu of x. Mu of x dy by dx plus mu of x p of xy equals mu of x q of x. We want the left side to be the derivative of mu of xy. d by dx of mu of xy equals mu of x dy by dx plus mu prime of xy. Comparing the two expressions, we need mu prime of x equals mu of x p of x. This is a separable ODE for mu. Mu prime divided by mu equals p of x implies ln mu equals integral of p of x dx plus c. Exponential both sides, the constant c can be taken as 0 because it only multiplies mu by a constant which later cancels. Mu of x equals e to the integral of p of x dx. Thus the integrating factor is simply the exponential of the antiderivative of p of x. Analogy: imagine you are walking on a moving walkway. The factor mu, the walkway speeds up or slows down exactly as the slope p of x demands, so that when you walk differentiate, you automatically account for the extra push or drag. Practical tip: when p of x is a simple polynomial rational function or trigonometric function, the integral is usually straightforward. If the integral cannot be expressed in elementary functions, you still keep mu of x as the formal exponential and proceed formally. Example: if p of x equals 2 divided by x, then mu of x equals e to the integral of 2 divided by x dx equals e to the 2 ln absolute x equals x squared. When q of x equals 0, the ordinary differential equation becomes homogeneous. dy by dx plus p of x times y equals 0. Multiplying by the integrating factor mu of x equals e to the integral of p of x dx gives mu of x dy by dx plus mu of x p of xy equals d by dx of mu of xy equals 0. Integrating both sides with respect to x, mu of xy equals c, where c is a constant of integration. Solving for y of x equals c over mu of x equals c e to the minus integral of p of x dx. Interpretation: the solution is a scaled version of the reciprocal of the integrating factor. The shape of the solution curve is completely dictated by p of x. Concrete example: consider the cooling of a hot metal rod in a room where the cooling rate is proportional to the temperature difference. dt by dt plus kt equals 0, Newton's law of cooling. Here p of t equals k, a constant. The integrating factor is e to the kt. The homogeneous solution is t of t equals c e to the minus kt, which matches the well-known exponential decay law. Everyday analogy: think of a ball rolling on a slippery hill that has a friction force proportional to its speed. No external push, q equals 0. The speed decays exponentially, exactly the form we derived. Explanation: for the non-homogeneous case q of x not equal to 0, the equation is dy over dx plus p of x times y equals q of x. Again, multiply by the integrating factor mu of x equals e to the power of the integral of p of x dx. d over dx of mu of x times y equals mu of x times q of x. Now integrate both sides. Mu of x times y equals the integral of mu of x times q of x dx plus c. Finally solve for y. y of x equals 1 over mu of x times the integral of mu of x times q of x dx plus c. The term containing the integral is the particular integral or particular solution, and the constant c gives the complementary homogeneous solution we found earlier. Step-by-step recipe. Number 1. Write the ODE in standard form and read off p of x and q of x. Number 2. Compute mu of x equals e to the integral of p of x dx. Number 3. Form the product mu of x times q of x and integrate it. Number 4. Divide the whole right-hand side by mu of x. Number 5. Add the constant c or determine it from an initial condition. Real-world example. A circuit with a resistor R and an inductor L driven by a sinusoidal voltage source V of t equals V sub 0 sin omega t satisfies L di over dt plus Ri equals V sub 0 sin omega t. Here P of t equals R over L and Q of t equals V sub 0 over L sin omega t, using the integrating factor mu of t equals e to the power of R over L times t, and following the steps yields the current I of t as a sum of a decaying exponential. A homogeneous part and a steady-state sinusoid particular part. Analogy: imagine a bathtub being drained, the homogeneous part, while a faucet continuously adds water at a varying rate, the non-homogeneous term. The water level finally becomes a mixture of the natural draining pattern and the contribution from the faucet. Explanation: an initial value problem IVP supplies one extra piece of information, usually the value of y at a specific x. Y of x0 equals y0. After solving the ordinary differential equation, we have a general solution containing an arbitrary constant c to determine c. We simply plug x0 and y0 into the solution. A procedure. Step 1. Obtain the general solution y of x equals 1 over mu of x times open parenthesis integral mu of x times q of x dx plus c close parenthesis. Step 2. Substitute x equals x0 and y equals y0. Step 3. Solve the resulting algebraic equation for c. Step 4. Insert c back into the expression for y of x. Example: solve di over dx plus 2 over x times y equals sin x over x, with the condition y of pi equals 0. P of x equals 2 over x, q of x equals sin x over x. Mu of x equals e to the integral of 2 over x dx equals x squared. Multiply and integrate. D over dx of x squared y equals x squared times sin x over x equals x sin x. Integrate. X squared y equals integral of x sin x dx equals negative x cos x plus sin x plus c. Solve for y. Y equals open parenthesis negative x cos x plus sin x plus c close parenthesis over x squared. Apply y of pi equals 0. 0 equals open parenthesis negative pi cos pi plus sin pi plus c close parenthesis over pi squared equals open parenthesis pi plus 0 plus c close parenthesis over pi squared. Hence c equals negative pi. Final solution. Y of x equals open parenthesis negative x cos x plus sin x minus pi close parenthesis over x squared. Why it matters? In engineering, an IVP corresponds to a system that starts from a known state. For example, a capacitor initially uncharged, and we want to predict its future behavior. Explanation: when the coefficient p of x is not a constant but a function of x, a variable coefficient, the same integrating factor method still works. The only difference is that the integral of p of x dx may be more involved. Illustrative example 1 - air cooling of a pipe : the temperature T of a fluid flowing through a pipe loses heat to the surrounding air at a rate proportional to the temperature difference and to the local surface to volume ratio, which varies with the position x : dt divided by dx plus k over 1 plus x squared times t equals 0. Here p of x equals k over 1 plus x squared. Compute the integrating factor : mu of x equals e to the integral of k over 1 plus x squared dx equals e to the k arctan x. Multiply and integrate : derivative with respect to x of e to the k arctan x times t equals 0, implies e to the k arctan x times t equals c. Hence t of x equals c e to the negative k arctan x. Illustrative example 2 - variable resistance RC circuit : suppose a resistor's resistance changes with time as R of t equals R naught left parenthesis 1 plus alpha t right parenthesis. The voltage across a capacitor satisfies dV divided by dt plus 1 over R of t times C times V equals E of t over R of t times C. Here P of t equals 1 over C R naught left parenthesis, 1 plus alpha t right parenthesis. The integrating factor becomes mu of t equals exponential of the integral of dt over C R naught left parenthesis, 1 plus alpha t right parenthesis, equals exponential of 1 over C R naught alpha times natural log of absolute value 1 plus alpha t, equals left parenthesis 1 plus alpha t right parenthesis, raised to the 1 over C R naught alpha. Proceed as before. Step by step for variable coefficients : Step 1, write the equation in standard form. Step 2, identify P of x. Integrate it, use substitution if necessary. Step 3, exponentiate to obtain mu of x. Step 4, multiply the whole owed by mu of x. The left side collapses to a derivative. Step 5, integrate the right side, may require integration by parts or special functions. Step 6, divide by mu of x and add the constant of integration. Analogy: think of a car whose friction coefficient changes with road condition, wet, dry, gravel. The same braking formula works, but the factor that represents friction now depends on the distance traveled. We adjust the braking efficiency, the integrating factor, accordingly. Solve the differential equation. dy by dx minus 3 over x times y equals 2x squared, y of 1 equals 5. Step 1, standard form. The equation is already in the form dy by dx plus p of x times y equals q of x, with p of x equals negative 3 over x, and q of x equals 2x squared. Step 2, integrating factor. Mu of x equals e to the integral of p of x dx, which equals e to the integral of negative 3 over x dx, which equals e to the minus 3 ln absolute x, which simplifies to x to the minus 3. So mu of x equals 1 over x cubed. Step 3, multiply equation. 1 over x cubed times dy by dx minus 3 over x to the fourth times y equals 2x squared over x cubed, which simplifies to 2 over x. The left-hand side is the derivative of y over x cubed, that is, d by dx of y over x cubed equals 2 over x. Step 4, integrate. Integrate both sides with respect to x. Y over x cubed equals 2 ln absolute x plus c multiplied by x cubed. Y of x equals x cubed times parentheses 2 ln absolute x plus c close parentheses. Step 5, apply the initial condition. Set x equals 1 and y equals 5. 5 equals 1 cubed times parentheses 2 ln 1 plus c close parentheses, which equals c because ln 1 is 0. Hence c equals 5. Step 6, final answer. Y of x equals x cubed times parentheses 2 ln absolute x plus 5 close parentheses. Interpretation. The solution consists of a homogeneous part cx cubed, which would exist even without the right-hand side, and a particular part 2x cubed ln absolute x that reflects the influence of the source term 2x squared. The initial condition selects the specific trajectory starting at the point 1, 5. Engineering viewpoint. This type of equation appears when modeling the temperature distribution in a rod whose conductivity varies with position. The term 2x squared could represent a spatially varying heat source, while the minus 3 over x factor accounts for a radius-dependent heat loss. Short answer: 1 line, identify P of x and Q of x question. Write the standard form of dy over dt plus y over t equals sine t and state P of t and Q of t strategy. The equation is already dy over dt plus P of ty equals Q of t, hence P of t equals 1 over t, Q of t equals sine t. Multiple choice integrating factor. Question. For dy over dx plus open bracket 2x close bracket over open bracket 1 plus x squared close bracket y equals e to the x, the integrating factor is a e to the x squared, b open bracket 1 plus x squared close bracket squared, c e to the ln of open bracket 1 plus x squared close bracket, d open bracket 1 plus x squared close bracket to the minus 1. Strategy. Compute mu equals e to the integral of 2x over 1 plus x squared dx equals e to the ln of 1 plus x squared equals 1 plus x squared. The correct choice is B after squaring, since e to the ln of 1 plus x squared equals 1 plus x squared. Long answer: solve initial value problem. Question. Solve dy over dx plus y over x equals x squared with y of 2 equals 3. Strategy: first, identify p of x equals 1 over x, q of x equals x squared. Second, integrating factor mu equals e to the integral of 1 over x dx equals x third. Multiply to get d over dx of open bracket xy close bracket equals x cubed. Fourth, integrate to get xy equals x to the fourth divided by 4 plus c fifth. Solve for y gives y equals x cubed over 4 plus c over x sixth. Apply y of 2 equals 3. 3 equals 8 over 4 plus c over 2, which gives c equals 2. Seventh, final answer. Y of x equals x cubed over 4 plus 2 over x. Conceptual: when does the method fail? Question: which of the following equations cannot be solved by the integrating factor method? A. Y prime plus sine xy equals cosine xb, y prime plus y squared equals xc, y prime minus 2 over xy equals e to the x strategy. The method requires the equation to be linear in y, no y squared, exponential of y, etc. Option B is nonlinear, so it cannot be solved by this technique. Quick check: verify a solution. Question: verify that y equals 1 over x plus x squared satisfies dy over dx plus 2 over xy equals 3x strategy. Compute dy over dx equals negative 1 over x squared plus 2x, then dy over dx plus 2 over xy equals open bracket negative 1 over x squared plus 2x close bracket plus open bracket 2 over x close bracket times open bracket 1 over x plus x squared close bracket equals negative 1 over x squared plus 2x plus 2 over x squared plus 2x equals 1 over x squared plus 4x, which would equal x only if 1 over x squared equals negative x, which is false. Therefore, the proposed function is not a solution. This quick substitution check works. Tip for exams: always write the standard form first, then list p of x and q of x after that. Compute the integrating factor in a separate line. This prevents algebraic slips. When an initial condition is given, plug it in after you have the full expression for y. Do not try to determine c earlier.